Scott here, going to go over the Chapter 7 review. This is for Chapter 7, all of the modules except for 7.5. So I'm not really going to hit that because we haven't talked about other distributions in this course. So let me start this here. And the first question that we are looking at here is the picture of a distribution. And this is in the version of like a histogram. So we have to just think about what this shape of this distribution looks like. And so we can see our options here of there's symmetrical but not uniform. Well, that could be close here. We've got skew to the left, skew to the right, and I'm going to go ahead and say uniform because we're mostly on that straight line there. And let's see if we're correct. Yes. Okay, so questions like that, identifying our distributions. Then we're also going to have questions where we're needing to indicate on the curve where the given x value should be. So this is going to help us determine where different data observations in our data set would fall along our distribution curve. So for this one, I'm given an x equal to 83.4. I have a population mean, a mu of 83.1, and then a standard deviation or sigma at 1.3. So I'm looking for 83.4, and for these, it's actually like a little slide. So I can go from the mean is where they start me at. I need to go and find 83.4, and that's the marker of my x value as they've given to me. So I'm going to submit that there, and we see that's right. So those are going to be moving of the slides in order to get where that x value is. Now, this next one is going to be a little bit trickier, but it's also looking at the distribution of um, our data set, and then it's on a what's called a probability plot. And for this one, it's going to be our closest one to the line. And so that is going to be our normal distribution is indicated there as it's going along that line of best fit. All right, now for this one, it's asking us to find the value of z such that 0.14 of the area lies to the right of z. We'll round our answer to 2 decimal places. There is at least 2 different ways to do this. We just have to really realize what that question is asking us. So my area to the right of z is actually asking us for like the upper part of our distribution. But our table really only gives us not, yeah, it only gives us the area to the left. I said that with way too many words. It gives us the area to the left of our z always. So in order to get the area to the right, we have to do a couple of different manipulations. Here, it's already giving us the area, and what we need to realize is that that is the top of our distribution curve, but the table is going to give us the bottom of our distribution curve. So one thing that we can do is we can actually subtract that 0.14 from 1. And so I'll show you that here in this B3 cell. Pop that up. I'm starting my equation 1 minus 0.14. And so that gives me a value of 0.86. So that's the value that's going to be on the table. So when I look at this here, I can go to the table. Here it's provided for me a couple options for the table. If I also click on here, I can go to standard normal table, and it's going to give me essentially these same options. What I want to do is I want to look for my positive infinity. If I've got 0.86, if I have anything above zero point 0.8 or zero point 0.5, I know that I'm in this upper or the positive z table. So now with this particular question, it's telling me my area lies to the right. This is the area. On this way that we're doing it, I'm actually looking for my 0.86 that I calculated by subtracting this from 1 because the area to the right. My table only contains the area to the left, so that's why I'm looking for 0.86. Now, Hawks is funny in that on these where it's really close, normally the rule of thumb would be to go under. Hawks just want you to find the closest one. So right here, I've got 0.8599, and this is going to be my closest value to 0.86. I'm going to go out to the edges here, and I've got 1.0 and zero point zero 0.08. So my answer is going to be 1.08. And now I'm going to talk you through the other way to do this. So with seeing this 0.14 and knowing about our normal distribution and having it be symmetrical, meaning that at the mean we are split into two identical distributions or areas under the curve, if you want to think about it like that. So I could take this 0.14 and I could find this value and I could inverse my z value. So if I'm looking for 0.14, it's going to be in my negative side there. And on this way, I'm looking again for 0.14, or now I'm looking for exactly 0.14 or as close that I can get to it. So it looks like this is going to be my closest to exactly 0.14. So if I click here, now I'm looking at negative 1.0, and then as I go up, I'm at 0.8. Now this is the area to the left of that value. But again, my normal distribution is mirrored, and so if I flip this sign, then I know that 0.14 percent or area under the curve is going to be to the right of a positive 1.08, which is what we already had. Now to do this in Excel, I've got that 0.86. I'm going to also need that as I'm calculating. Again, Excel and our statistical tables always work with that area to the left, and so that's why I need that. Here in B4, I'm going to start the formula to find the z value for a given area under the curve. I'm spending a lot of time on this, I know, but hopefully it'll be valuable to you. For finding the z value when I'm given an area under the curve, I need to use my norm.s.inverse. So what that's going to ask me for is the probability. Well, what's the probability? There's a lot of different terms for this. Area under the curve, area, probability, percentage, all of those things will be sort of called, they'll be called these different things in the course of all the questions that you read in statistics. In Excel, it's called probability. In the statistical table, it's called area under the curve. I don't particularly know why we have all these different names for the same thing. Here I'm going to put in 0.86 because again, Excel works from that to the left of my z value. And so I need to do that subtraction of that area to the right. 1 minus the area that I'm looking for to the right gives me my area to the left. And so I've got 0.86. Now the norm.s.inverse of 0.86 is 1.08. So there's two different ways that you can go about solving a problem like this one. Let's go ahead and submit that. Oh, after all of that. Oh no, it switched it. I see what happened. It switched it back to that negative when I was trying to show that different way. Okay. So 1.08, and I'll submit that, and there we go. Okay. The other types of problems that you're going to see here, I'll just do a few more. That is really the bigger one that you're going to run into and have some issues with. Here we go. This is looking at two normal distributions plotted on the same x-axis. And it says, what statement best describes this graph? So we can have, we've got the same mean, it looks like, because that's where they are both in the center of but we have slightly different standard deviations when we're going out from them. So we have two distributions have equal means and standard deviations that differ by 10 units. We have two distributions have equal means and equal standard deviations. Well, if that was the case, they would be exactly one another. Our standard deviations that differ by 10 units. I don't know if this is exactly 10 units in difference for our standard deviations, but they're definitely different standard deviations, right? Um, the two distributions have equal standard deviations. Well, not necessarily, because then they would look exactly the same as they're billowing out. These two distributions have equal means and different standard deviations. So again, our standard deviations mark that standard distance from the average or from the mean. So that kind of creates what our normal distribution is going to look like. So this one right here is going to be our last option because again, our means are the same along that 10, but our curves are shaped different, and that means that our standard deviations are different. Okay, now this one is another one like we did with the area to the right. Now it's going to be a little bit more straightforward because it's just asking for the area that lies to the left of Z. So whenever you see any value or area that is below zero point 0.5, then you know that in Hawks you're going to be using this negative Z table. And so I'm looking for this 0.05 inside the table and going to go out to look for that Z value. And this one right here, it's going to fall in between. So I see this at 0.0495 and I see this at 0.0505. And it's going to be that right in between distance, but we'll see what they can let us get away with because these are equally um, away from 0.05, and I've got negative 1.6 and 5 and 4. So it's really in between that. Let's see if they say we'll be good with a negative 1.65. I'll try that one first here. And yes, that is correct at that negative 1.6. They should also give it to you for 4.5. How will we do that in Excel? Again, this is my area to the left, so let me delete these that I had in there before. I'm just in V3 just because I'm picking a cell. This is my norm dot s dot inverse again, and it's asking for the probability. In the question, it's asking us for the probability to the left, so that's what Excel and what our table is set up to give us. I give 0.05 and I start that here as I press enter, then I'm given this value of negative 1.64485. So it would technically be negative 1.645 is how it's really used in statistics. And I guess here they'll take either 1.64 or 1.65. They should anyway. Let's go to the next one and see what that one looks like. Here we're getting a little bit more complicated, but as we can see here, draw a diagram below is an illustration of the empirical rule. So our empirical rule is with our standard deviations away from the mean, and this is asking us about how many standard deviations would we expect, or sigmas would we expect to be from the mean and to be covered like this. So a few things that we can do just in seeking this out, if we really wanted to prove that. In the tables on Hawks, they actually give us an infinity or a zero from the mean to the z value. And this is only helpful in a few instances. I don't really want to confuse you with this, but it might be helpful in a situation like this. So here it's got 0.4772, and that's my area under the curve. and it's asking for what would this z value be, or that distance divided by standard deviations. So if I've got that 0.4772, I can go to this particular table, my 0 to z, and that's giving me the distance from my mean on a standard normal distribution is 0 out to whatever z value it is. That's what this table has given us here, that 0 to z. So in any other circumstance, make sure that you are not clicking on that 0 to z. But for this instance here, we can do that. So at 0.4772, if I find that in my table, it's right here at 2.0 and 0. So that is exactly two standard deviations away from the mean. So that is my mu plus 2 sigmas. I'll submit that there. And that's how we've got that one. And so there's more distribution comparisons. There's one other that I want to show you, and it's right here. So here we're going to calculate the standard score of the given x value. X is equal to 40, where my mean is equal to 36.3 and my standard deviation is equal to 39.8. Now there are also two ways to do this one. And one is with the equation, and then one is with an Excel function. So I'll show you the first way with the equation, just back again in this B3 cell. My equation is my x value minus my mean divided by my standard deviation, or in terms of Greek letters here, my x minus my mu divided by the sigma. So I'm going to start my parentheses, and I'm going to say my 40 is my x value, subtracting my mean, which is 36.3. I'm going to close that parentheses, divide by my standard deviation, which in this case is 39.8. That might be an error on their part because that standard deviation looks pretty huge. Okay, so I'll go ahead and enter in this, and I've got a standard score, or a z value as I usually call them, of 0.09. So that's just meaning that we are super close in terms of standard deviations to our mean. Another way that we can do that with Excel functions is this standardize. And so what standardize, it tells you what it's asking for, the x, it's asking for the mean, and it's asking for that standard deviation. So all of those have been given to us in the problem. We've got the same values we just used in that other equation. My x is 40, that mean was 36.3, and then my standard deviation was given at 39.8. And I should get that same value of 0.0929. So I'm going to put that in here, 0.0929, and let's see if we've got that answer correct. Yes, we do. All right, so this was a not so short as I meant run through of the Chapter 7 review module homework.